today we're going to work through section 6.1, which is somewhat a little bit of a review from last year in Algebra 2. We're talking about systems of equations and inequalities. A system of equations is when we have two or more equations with the same variables. So this could be something like x plus y equals 5 and 3x plus y equals 6. That could be our system. Or we could have something a little more involved, a little more complicated with more variables and more equations. Something maybe like 3x plus 2y plus 7z equals 10. X plus y minus z equals 6, and then 5x plus y equals 14. The rule of thumb is however many variables you have, that's how many equations you have to have. So if you have two variables, you have to have at least two equations. 5 variables, 5 equations. We're never really going to reach 5 variables, 5 equations, but we'll see a lot 2 variable and 3 variable systems. So solutions to a system of equations is typically thought of as being a coordinate point. So either one or more coordinate points depending on what sort of system we have, and those are where those two lines or the two graphs or the planes intersect. And that solution, that one point of intersection, needs to be true for all the equations, for all the lines. So if I'm looking at two lines here and here, this point where they intersect, that would be my solution. So that we typically write solutions to our systems as coordinate points. So 1, 5 or 3, 6. You can, if you're dealing with 3 equations with 3 variables, you can have an ordered triple, and then it would be graphed in 3-dimensional space. We're not really going to look at those graphs so much. If we're going to be asked to graph to look at an equation or to look for the solution to a system of equations, it's going to be just the 2 lines. So not every system is going to have a solution. Some of our systems will have no solution. So no solutions are where your 2 lines are parallel. So something like these 2 lines here, you can see that as they're graphed, they're going to run next to each other infinitely, and they're never going to intersect. So there's no shared points. There's no point that works for both lines. So we'd say there's no solution here. If I look at these as their slopes, they both are going to have a slope of -1. And so that's some way to indicate that we're not going to have a solution to our system, as we have a slope of -1. My second system here intersects exactly at once. So there's one point of intersection here. So we say there is one solution. And if I'm looking at just 2 lines, there's only ever going to be one solution if a solution exists, except for one special case where we have the same line. So if we have 2 distinct lines, there's one solution because there's only one point of intersection for 2 different lines. And here we have 2 different slopes. One of my slopes is -1, and one of my slopes here is +1. So the 2 different slopes indicate that it's going to be one point of intersection. Our last possibility is if we have our 2 equations are actually the exact same equation. They are the same exact line. And then in which case when you graph them, it's going to graph right on top of it. So they have all of these shared points of intersection here. So we have all of these potential solutions. We don't just have 1 or 2 or 3, but we actually have an infinite number of solutions. So we would write that there's an infinite number of solutions. So when you have a system, especially a system of 2 lines or 2 linear equations like we have here, you can have a no solution, one solution, or an infinite number of solutions. So methods of solving them, there's a couple different ones. Graphing isn't one we typically use to solve. We use this more so to check solutions. So to check something, we can quickly graph it on our calculator and make sure that that point of intersection is the point that we found using mostly either elimination or substitution. So we use these two here when we have just two equations with two variables. So typically an x and a y. This last one, this RREF, row reduced echelon form, is also called the Gauss-Jordan elimination method, which you may see in your homework. This is when we have our three variables or more. So we could have three variables or three equations, or we could have even more. We could have 4, 5, 6. And this is when we use the matrix functions on our calculator. And we'll talk more about that later, most likely in the next video. But we've got our matrix function on our calculator, and we use this with our three variables and our three equations. So today we're going to focus on just elimination and substitution, and then using the graphing function on our calculators to check. So this first system here we're going to solve using substitution. And substitution works really well when you have a coefficient in one of your variables being 1. And we actually have that in both equations here. Both equations, the x has a coefficient, oops, can't really see that, of just being a 1 there. So it's easy for me to either solve the first equation for x or to solve the second equation for x and then substitute into the other one. So I'm going to take this first equation here and I'm going to solve for x. So I'm going to move that negative 4y to the other side by adding 4y. So I get x is equal to negative 11 plus 4y. And what I can do is I can take that equation there and I can solve, or excuse me, I can take this right here and I can plug that in to the x in the second equation. So I can rewrite that second equation. Instead of x plus 3y, I can write negative 11 plus 4y plus 3y equals 3. So this x that we have here, oops, that highlighter does not work very well. This x that we have here has now been replaced with this entire expression. But I now have an entire equation with just y's, and I can solve that just like we've been doing for a really long time. We got negative 11 plus 7y equals 3. Add 11, we get 7y equals 14, so y equals 2. And the last thing I need to do is I now need to take that and go plug it back in. And I can plug it into any of my equations. I usually like to plug it back into the one that's solved for x, because then I don't have to do any adding or subtracting to two sides. But you can plug it into any of the equations and you should get the same thing. So here I'd get, oops, 2. Negative 11 plus 4 times 2, or x equals negative 11 plus 8. So x equals negative 3. Then the last thing I do is I would want to write that as a coordinate point, negative 3 comma 2, or I can list them off, x equals negative 3, y equals 2. Either way is fine. So that would be my solution. So my solution, that shared point of intersection between those two lines would be negative 3 comma 2. So we can check that on our graph. So we can go to our graphing calculators. Now the thing with the graphing calculators, it has to be in that y equals mx plus b format. So you do need to solve both equations for y, and you are going to get those fractions in there when we do that. So that first equation there becomes, we subtract the x from both sides, we get negative 4y equals negative 1x minus 11. And then dividing everything by negative 4, I get 1/4 x plus 11 over 4. So we want to make sure we have those parentheses in there when we type it into our calculator. And then the second equation, we also need to solve that for y, excuse me. So I get 3y equals negative 1x plus 3 y equals negative 1/3 x plus 1. When we graph it in our calculators, we can use the intersection function on our calculator. So we can hit second trace where it says calc up in blue right above that trace button. We can hit second trace, and then intersection is one of those options for us. It's number 5, and you can choose both graphs and you can guess, and it'll give you that point, and it'll have it listed down at the bottom. So it should match that values that we had before, and it does. So our intersection, our solution to this system is x is negative 3, y is 2, or the coordinate point negative 3, 2. So I want you to try, we're going to do this one together. I forgot which one this was. We have y is equal to x cubed minus 3x squared plus 4, and y equals negative 2x plus 4. This time we don't have two linear equations. We have a cubic function and a linear equation, which means most likely we're going to have more than one solution. Not an infinite number of solutions, but that line can now intersect that cubic function more than just the one time. Two lines can only intersect at one point, but with a cubic function, because it curves, our line could intersect it more. The nice thing about this one is it's already solved for y, so I don't have to do any solving before I can go straight to my substitution. So I can take this entire first equation and I can plug that in for the y down below, and I can get my x cubed minus 3x squared plus 4 equals minus 2x plus 4. And I want to solve this for x. And so when we don't have a linear equation, when we have our exponents higher than 1, so an exponent of 2 or 3, and you're asked to solve it, we're going to factor, but we have to set it equal to 0 first. So the very first thing I have to do is I have to add 2x to both sides, and I don't actually have anything to add it to on the right. There's no like terms. And I have to subtract the 4, and that I do have a like term that I can combine together. But once I do that, I get a new equation. I get my x cubed minus 3x squared plus 2x, and then the 4's cancel, and it's equal to 0. Once it's set equal to 0, now I can go and factor, and I want to start by factoring out any GCF, the greatest common factor that I have, which in this case is going to be an x, and then I have x squared minus 3x plus 2, and then I'm left with just this quadratic inside that parentheses there that I do want to solve. I do want to factor as well. So I want to look at that, and you can factor it a variety of ways. I use the AC method, and so I would look and say, okay, well, I've got my AC is 2, negative 3 is b, that's what I want to add to, so I would choose negative 1 and negative 2. So I still have the x out in front, but that quadratic, that trinomial now becomes x minus 1, x minus 2 equals 0. So I get x equals 0, x equals 1, x equals 2. And those are my 3 x values. And so I have to take all 3 of those x values individually, and I have to plug those back in for my y values. So I'm going to start with the x equals 0. When x equals 0, I do have an... Alright, so I hope that you're able to get this. There's a lot of work involved, a lot of algebra behind all of it. But you start off, I would recommend taking that second equation and substituting or solving that one for y. That one's going to be a little bit easier for us to work with. So that's this equation here. And then I can quickly, or maybe not so quickly, but I can easily get that y alone, at least compared to the one on the first equation. And I get 2x plus 1, and I can take that and I can plug that in for the y up in the first equation, and I'm left with this. And it is really important that I have those parentheses, because I need to make sure that I'm subtracting that entire expression and not just the 2x, but I need to make sure I subtract the 1 as well. But after that, once I get to this point here, I do the exact same thing we did before. You're going to combine all your like terms, and you want to move that 7 over because we want to make it set equal to 0. and then we have to factor it. Now this one takes a little bit more time to factor it, but again, I use the AC method. There's a lot of ways that you can factor. When we want to factor, we get down to our two x values down here, and then we just have to go and plug them back in, and I get, when I plug them in, and I'm going to plug them back into that bottom equation, the one that's solved for y, a little bit easier than the 2x minus y equals -1, and a lot easier than the 3x squared plus 4x minus y equals 7. Don't have to square anything. But I plug that 4/3 in, and I get 5/3 out. Plug the -2 in, I get -5 out. And again, we can check our answers by graphing. Oops. But we can check our answers by graphing. I don't have it up there, but you can definitely check it when you're graphing. Number 4, I want you to, again, try it on your own. Pause the video, try it for a second, and then come back and see how you did. All right, so if you tried this and you substituted that 4 plus x back in for that bottom equation of y, you should have ended up with something like this, and then you probably got stuck. You may have tried your factoring, you may have tried to do that AC method or the magic x method, and we would have gotten that we're trying to multiply to be 1 and add to be 1. And we might think, oh, that works because when you multiply 1 times 1, you get 1. But 1 plus 1 gives us 2. And so as it is, this expression, this equation here, has no solutions. There is nothing. There is no two numbers that multiply to 1 and add to 1. So it cannot be factored. So there isn't any solution. There are no x values that I could use that would give me 0 back. So here we would have no solution. If I were to graph these two equations would never intersect with each other. Our last one here that we're going to look at are our application problems. And so these are our word problems. And when you have your word problems, you want to make sure that you first read the problem very carefully. It is really important that we read through it carefully. It's easy to miss things if we skip around or if we just skim, but you want to read through it carefully. And then what we want to do is we want to find any quantities that we're asked to look for, and those are going to be our variables. And we want to define those variables. We want to write out x equals this, y equals that. So we have a clear understanding of what it is we're looking for and how we can then write our equations. Because that's the next thing that we're going to do. We're going to write our equations. We're either going to write 2 equations if we have 2 quantities, 2 variables we're looking for, or 3 equations if we have 3. So however many variables is going to tell me how many equations that I need. Because we need at least 2 equations, we're going to look for we need at least 2 equations. We're going to look for 2 or more statements or facts, things that they tell us about those unknown values. So if we're talking about bank accounts, how many bank accounts do we have, and what's the total amount that's being invested or being put into those bank accounts? If we're doing some sort of sales, what is the amount that we sell each item for, or how much does each item cost to make? Facts that we have about those unknowns, that's what's going to help me write my equations. 2 quick things, especially if you're dealing with some sort of a business or you're dealing with sales and profit. Your break-even point is when the amount that you spend, your cost, is the same as the amount of the revenue, the amount of money that is coming in. So that usually is in the sales. So depending on how much things cost, how many you sell, that's going to give you your revenue. And then the cost is how much it takes to make. So there's usually a sunk cost, a fixed amount that's involved. It's the investment. It's what it goes into the production. It goes into rent for a facility and salaries for your employees. That's like a fixed cost. And then you have a cost per item. So that includes the materials and the individual labor and all those things. So your break-even point is when your cost and your revenue are equal. And then anytime we're talking about profit is the money that you take home in the bank or you put in your pocket, and that's always going to be the revenue, the amount of money that's made through selling the items minus the cost. So two things when you're dealing with sales there. So we've got this first one here. We've got a shoe company. They're investing $300,000 in equipment to produce a new line of athletic footwear. Each pair of shoes costs $5 to produce and is sold for $60. This $300,000 is a sunk cost. That is a fixed amount that's never going to change, but it is part of the money that you had to invest into the company. That's part of your cost. And then the other part of the cost is this $5 per pair of shoes. So that's going to change depending on the number of shoes that we sell. Like if you sold 10 pairs, then that's $50 in cost. If you sold 100 pairs, that's $500. So that's gonna adjust a little bit depending on what your number of shoes is. But the $300,000, that's a fixed one. And then the selling price, that $60, is going to go into our revenue. So we're going to start with our two variables, or one variable. Our variable here, X, is going to be the number of shoes. And then we're going to look at a couple other variables, specifically our cost and our revenue. And we're going to write equations for those two. So those are our costs, our two other variables. C is going to be the cost, and R is going to be the revenue. And so I want to write an equation for cost. And my cost is going to include that $300,000. That's a sunk cost. That's not going to change. No matter how many pairs of shoes I sold, I've already spent $300,000. But then for every pair of shoes I sell, I have to spend another $5. So my cost is going to be $300,000 plus 5x. My revenue, the amount of money that comes into the store, is going to be for every pair of shoes. So for every X, I sell it for $60. So my revenue would be 60x. So I have a cost function, I have a revenue function. I want to know, when do I break even? So break even is when your cost is equal to your revenue. So this would be like a substitution. We're going to substitute in C for R. More specifically, we're going to substitute in the $300,000 plus 5x in for R and make that equal to 60x. So we can solve and we can subtract 5x from both sides and then divide by 55, and we should get $5,454.5 pairs of shoes. But there's a problem. I can't sell 0.5 pairs of shoes. So what we're going to do is instead we're going to round up, and we're going to say we sold 5,455 pairs of shoes. So that's how many pairs of shoes it's going to take till we break even, till the amount of money that we've made matches the amount of money that we spent. Part B is asking for how many pairs of shoes do we have to sell to make a profit of $80,000. So we have the same two equations, we have the same variables here, but now we're asking about a profit. And remember, profit is going to be our revenue minus our cost. So the money coming in minus the money going out. So my profit, I want that to be my $80,000. I want to make $80,000 in profit. And so that's going to have to equal my revenue, my 60x, minus the cost of $300,000 plus 5x. And again, the parentheses are really important. I need to make sure that I have that. So I'm subtracting that entire cost function. So I can distribute that negative sign, and I get 60x minus 300,000 minus 5x, and I can combine my like terms, get all my x's together, all my non-x's together, and I get 380,000 equals 55x, and then dividing by 55 on both sides, we get that the number of shoes we have to sell is 6,909.09. But just like above, oops, the decimal doesn't go there, 6,909.09. But just like above, that decimal, I can't sell 0.09 pairs of shoes. And if I were to round this down to 6,909 pairs of shoes, I wouldn't quite reach that $80,000 mark. So to make sure I actually hit the $80,000 mark, I'm going to round up and make this 6,910 pairs. So my profit is going to be more than $80,000. But if I were to round down, I would have been just underneath that goal of $80,000. So remember, break even, cost is equal to revenue. Profit is going to equal your revenue minus cost. Our, I think, last example, we've got an investment here. We're investing $12,000 into 2 different bank accounts. One account is going to pay $5,000, or excuse me, 5% interest, and the other is going to pay 3% interest. $5,000 would be a great bank account. You don't have that here. And then we have a yearly interest rate. How much interest we make on the 2 accounts together is $500. And so we're trying to figure out how much got invested into each account. So we're going to have 2 different variables. We're going to have an X variable and a Y variable, and they're going to represent the different amounts in each account. So there's 2 different amounts that I'm trying to find. One that goes into each account. So that's my 2 different variables. So I want to start by writing that out. I want to write out that my X variable is going to represent the amount of money in, let's say, the 5%, and then the Y is the amount of money in the 3%. And so I've written my variables, I've said what they are. What I want to do is I want to go back and I want to look for facts about those 2 quantities. That's going to help me write my equations. So the first fact is I have a total of $12,000 that's being split into the X and the Y. So my first equation can be, well, if I take X and I add Y, I have to get that total of $12,000. There's my first equation. The second equation is going to come from this interest rate. My interest rate is $500, and that's on both combined. So if I take the interest that I would get on the X amount and I add the interest I get on the Y amount, I have to get $500. So the interest that I earn on the X amount is going to be 0.05X, and the interest I get on the Y amount is 0.03Y, and adding those together has to give me my $500. So right now, right here is my system of equations, and I want to solve. And so you can use your substitution, or if you remember elimination, you can do that as well. I'm going to do substitution. So I can take that top equation and quickly make this X equals 12,000 minus Y and plug that into that bottom equation. So I have 0.05X, but I don't want X anymore. I have 0.05 times 12,000 minus Y, plus 0.03Y is equal to 500. Distribute the 0.05. 0.05 times 12,000 is 600 minus 0.05Y plus 0.03Y equals 500. By your like terms, we get negative 0.02Y equals negative 100. Subtract the 600 from both sides. And I get that my Y has to be $5,000. So my Y is $5,000. I can plug that back into that top equation, any of the equations actually, but I can plug it back in and I can quickly get that my X then has to be equal to 7,000. And these are monies, this is accounts, so I get $7,000 and $5,000. And I can write this as a ordered pair, or I can write it as X equals $7,000, Y equals $5,000. Okay, so those are my 2 accounts. we do have one more example. This last example does talk about, again, if you're selling something, if you're producing something, if you're manufacturing something, sort of how can we figure out what's the best amount, what's the optimal amount, or what's the optimal price. So what we've got a supply and a demand function. We have these two different functions here. And they're both in terms of X, which is the number of items being made or the number of items being sold. And then we have our P, which is the price that we would sell them at. And so what we're doing is we're looking for an equilibrium point. And an equilibrium point is when when your supply and your demand are equal to each other. So that's what we're going to do here. We're going to set supply equal to demand. So I get 150 minus 0.00001x equals 60 plus 0.00002x. And I just want to make sure I'm being really careful with those decimal points that I include all of the zeros. There is a way around it. You can multiply by a factor of 10, by enough 10 factors of 10 that you can move those decimal points along. But then you'd end up with really large numbers. That 150 and that 60 would end up being these huge giant numbers. So you're going to be working with either really big numbers or really long decimals, either way. If I finish solving this, I do get that 90 is going to equal 0.00003x, or that x is going to equal, I'm going to make sure I get this right, so I'm going to divide this. 90 divided by 0.00003 gives me 3 million. So the optimal number of objects, or the number of personal assistants, personal digital assistants to be produced and to be sold, so that the supply and demand are equal, is at 3 million. And what I want to do is I want to go and I want to find the price that goes along with this. So I'm going to plug it back in. And again, since these are where the two equations are equal, I can substitute it into either equation. I can do it into the supply or the demand equation. It doesn't matter. And neither is particularly nicer than the other, except supply is addition instead of subtraction. So I'm going to do that one. So my price for supply is 60 plus 0.00002 times the 3 million. And it's really easy to forget a 0 in there, so make sure in your calculator being very careful. And I get that the price is 60 plus 60, or 120. Okay, so systems of equations, two or more variables. Well, if there's just two variables, we usually use either substitution or elimination, and you can always check your equations by graphing. Next section is when we're going to deal with more than two equations. So if you've got three variables, three equations, and how we can use our calculator and the matrix function to simplify that process for us.